Let me read the book by Lee Smolin. The title is Einstein's Unfinished Revolution, The Search for What Lies Beyond the Quantum. Chapter 1. Nature Loves to Hide. According to Albert Einstein, reality is the business of physics. Quantum mechanics has been the core of our understanding of nature for 9 decades. It's ubiquitous, but it is also deeply mysterious. Little of a modern science would make sense without it, but the experts have a hard time agreeing what it asserts about nature. Quantum mechanics explains why there are atoms and why those atoms are stable and have distinct chemical properties. Quantum mechanics also explains how atoms combine into diverse molecules. As a result, it is the basis for how we understand the shapes and interactions of those molecules. Life would be incomprehensible without the quantum. From the behavior of water to the shapes of proteins to the fidelity and the transmittal of information by DNA and RNA, everything in biology depends on the quantum. Quantum mechanics explains the properties of materials, such as what makes a metal a conductor of electricity, while another is an insulator. It explains light and radioactivity, and is the basis of nuclear physics. Without it, we wouldn't understand how the stars shine, nor could we have invented the chips or the lasers on which so much of our technology is based. Quantum mechanics is the language that we use to write the standard model of particle physics, which contains all we know about the elementary particles and the fundamental forces by which they interact. According to our best theory of the early universe, all matter, along with the patterns that eventually coalesced into the galaxies, was yanked into existence from the quantum randomness of the vacuum of empty space by the rapid expansion of the universe. I don't expect the reader to understand precisely what this means, but perhaps the words evoke an image. In any case, if this is right, then without quantum physics, there would literally be nothing except empty spacetime. Yet for all its success, there is a stubborn puzzle at the heart of quantum mechanics. The quantum world behaves in ways that challenge our intuition. It is often said that in quantum physics, an atom can be in 2 places at once, but that is only the start. The full story is far weirder than that. If an atom can be here or there, we must speak of states in which it is, somehow simultaneously both here and there. This is called a superposition. If you are new to the quantum world, you are undoubtedly wondering what it means for an atom to be somehow both here and there. Don't be discouraged if you find this confusing. You are absolutely right to wonder what it means. This is one of the central mysteries of quantum mechanics. It is enough for now if you just accept this as a mystery, to which we attach the term superposition. Later, we will be able to demystify it. Here is a first step. When we say that a quantum particle is in a superposition of being here and there. This is related to wave-like nature of a matter. For a wave is a disturbance that is spread out, and so it can be both here and there. We speak of elementary particles, but everything quantum, including atoms and molecules, is both a particle and a wave. Here is a taste of what that means. If we do an experiment that asks where an atom is, the result will be that it is somewhere definite. But between measurements, when we are not looking for it, it turns out to be impossible to project where it might be. It is as if the likelihood of or propensity of finding the particle spreads as a wave when we are not looking, but as soon as we look again, it is always somewhere. Imagine playing a game of hide and seek with an atom. We open our eyes or turn on a detector and we see it somewhere. But when we close our eyes, it dissolves into a wave of potentiality. Open our eyes again, and it is always somewhere. Another feature unique to the quantum world is called entanglement. If two particles interact and then move apart, they remain intertwined in the sense that they seem to share properties which cannot be broken down to properties each enjoys individually. We can stretch our imagination to apply these new concepts to atoms and molecules, which are too small to see directly. We must study them indirectly, and to do that, we employ large and complex measurement devices. Those measurement devices are part of the everyday, familiar world of large objects. One thing we can be sure of is that big, everyday things display none of the bizarre behavior quantum mechanics describes. A chair is here or it is there, never in a combination of such states. When we wake up in the middle of the night in a strange hotel room, we may be unsure where the chair is, but we can be sure it is somewhere. And after we collide with it in the dark, our future does not become entangled with its future. In the world as we experience it, cats are either alive or dead, even if they are locked in a box. When we open the box, the cat does not suddenly resolve from a combination of a dead and alive to dead. But if we find it dead, it will likely have been so for some time, as we will instantly smile. Ordinary objects appear to share none of the quantum weirdness of the atoms of which they are made. This seems obvious, but it raises a mystery. Quantum mechanics is the core theory of nature. As such, it must be universal. If it applies to an atom, it must apply to 2 atoms, or 10, or 90. And we have excellent experimental evidence that it does. Delicate experiments in which large molecules are put in quantum superpositions show us that they are just as quantum weird as electrons. For one thing, they diffract and interfere as waves. But then quantum mechanics must apply to vast collections of atoms that make up you or me or our cat or the chair in which she is perched. But it doesn't seem to. Nor does quantum mechanics appear to apply to any of the instruments and the machines we employ to imagine the atoms and reveal their quantum weirdness. How can this be? In particular, When we measure a property of an atom, we employ big devices. The atoms may be in superposition of states, and so be several places at once. But the measuring instrument always indicates just one out of the possible answers to the questions we pose. Why is that? Why does quantum mechanics not apply to the very devices we use to measure quantum systems? This is called the measurement problem. It has been controversial and unresolved since the 1920s. The fact that after all this time we have found no agreement among experts means there is something basic about nature we have yet to understand. So there is somewhere a transition between the quantum world, in which an atom can be several places at once, and the ordinary world in which everything is always somewhere. If a molecule made from 10 or 90 atoms can be described by quantum mechanics, but a cat cannot, then somewhere between the two there is a line delineating where the quantum world stops. Our answer to the measurement problems would tell us where that line is and explain the transition. There are people who are sure they know the answer to the measurement problems. We'll meet some of them and their ideas later on. We will want to look out for what prices we have to pay for expunge this quantum insanity from our understanding of the world. Let me stop here and read later.